Alright, so moving on now, we're going to be covering in this video and the following videos the concepts of work, energy, and power. And so for a more condensed summary, we're going to be looking at more specifically work, kinetic and potential energy, as well as their differences, the work-energy theorem, power, the concept of power, conservative forces, Hooke's law, the conservation of mechanical energy, and energy diagrams. But more specifically in this video, we are for sure going to be looking at work, as well as the work-energy theorem, and we may dabble in some concepts of energy just as they pertain to the work-energy theorem. Our first concept is work, and so work is defined at least as a sort of infinitesimally small unit of work, dW, as the dot product between basically the net force acting on an object and the direction in which the object travels. So, just to illustrate that, if you have a dot, some sort of dot that travels along this path from, let's say, point A to point B, and it's pulled along by some force acting in this direction along this whole way, then basically you have two vectors here. You have the force vector acting this way, and you have, what's harder to see is this dr, this displacement vector, acting this way. So work is the dot product of the two. Therefore, it is equal to the force times the distances traveled, r, times the cosine of theta. In this case, theta is the angle between the force and the direction of travel. So you can see that if the force is perpendicular to the direction of travel, then cosine is 0 and no work is done. Likewise, if you have a force absolutely parallel to the direction of travel, cosine becomes 1 and you're simply just multiplying the force times the distance traveled. So just as a quick note about the units, you'll notice it's a force. So a force times some length x, which would be, if you're using the SI units, newtons times meters. But we know that newtons are kilogram meters per second squared. So this becomes kilogram meters squared per second squared, or we call this unit, we abbreviate it as the derived unit, joules, which is the unit for energy. And now, just as a quick side note about the force and how it works. Basically, if you have, from A to B, you have, let's say, it has this velocity vector because it's going from A to B. So, because of the nature of a dot product, if the force is acting, let's draw some quick axes as they relate to V. If the force is acting anywhere in here, excluding these endpoints, then it is doing positive work because it is adding to the kinetic energy, the velocity, the energy of motion of the object. Oppositely, if the force is acting anywhere in this area, so there, etc., then it is doing negative work because it's slowing down the object, it's acting in the opposite direction, and so it's sort of taking away kinetic energy from the object. You can never create or destroy energy, but you can remove it from this system of object by using this outside force in the form of work. Now, as a special case of this dot product, if the force is constant, so if force is constant, then what you can do is integrate this work integral instead of dw dot dr. You integrate both sides, and you get that the work done is simply the force dotted with the change in distance. And that's just for a straight line and a constant force. So how do we represent work graphically? Well, we have our definition of work, right? And, it's F dot dr. And then we can integrate both sides. But what if we just leave this side as an integral? So we get work equals the integral of f And if we're working in one dimension, we don't have to specify a vector, just a direction. So F times dx, basically, because we're operating only in the x dimension. Well, what this says is that the work is the area under the graph of a force. So over here we have the graph of force and distance. You can see as you increase your distance from the origin, the force gradually increases and then stagnates in here before once again descending. This area underneath this force graph is the total work. Just as with a force versus time graph, we got, the impulse J. It's the same thing except for, in this case, the force is position dependent, whereas with the impulse it was time dependent. Okay, so now we're going to be relating work and speed in part of what's known as the work energy theorem. So we'll start off with our definition of work, and what we can do is substitute instead of force, because we're looking at speed, we're going to be using ma, because this is just the derivative of velocity, and then integrating both sides with, instead of force, using ma, we get that the integral of work equals m times dv dt times dr. But we know that dr dt is simply the velocity, because it's the change in position with respect to time. So we can now substitute in a v for velocity instead of dr dt. So we get the integral of work now is m, which is constant, we'll just bring that out, times v dv. And now integrating both sides, you just get that work equals mv squared over 2. Oh, let's go from, say, v0 to v final, just arbitrarily changing our our initial and final velocities to represent any initial and final velocity. And what you end up getting is that work is mv final squared over 2 minus mv0 squared over 2. But what you should know is that this form, mv squared over 2, is what is known as the kinetic energy. Basically, it's a measure of the ability to do work in the motion of an object. So, because we have, work equals this final velocity or final kinetic energy minus initial kinetic energy, we can therefore determine that work is the total change in kinetic energy. And this is the definition of the work energy theorem, and it forms the basis for much of what we're going to be working on in the next few videos. So now we're going to do a sample problem. You can completely skip this if you feel you have an adequate grip, but I feel that practice always makes me understand the concepts better. So with that said, we're going to be answering a few questions about this situation right here, in which we have a block on some sort of tabletop being pulled by a rope at some angle theta, and the tabletop and block share this coefficient of friction mu k, and the block is pulled for some distance delta x. So what we want to know is the net force on the block, the net work on the block, what is the work done by friction right here, and the work done by the pulling force, F. And then if the velocity is constant, that's what this V equals K means, what is the net force, or net work rather, on the block? So, to start off by finding the net force, we'll do what we always do and draw a free body diagram. So we have F at some angle theta, we have the normal force from the table, the frictional force, as well as the weight, mg. So from here, to determine the net force, all we have to do is sum the forces in the x direction and sum the forces in the y direction. So, in this case, we can break up this force into its two constituent components based on this angle theta. So you have your Fy and your Fx, which equal F cosine theta and F sine theta, respectively. Now, you take your F cosine theta, subtract the friction, which is mu k times the normal, and for the forces in the y direction, it's basically just the normal, or rather, it's the normal force plus F sine theta minus the weight. Now, because the block isn't accelerating up or down, we know that the sum of the forces in the y direction is 0, or that the normal force equals mg minus F sine of theta. We can then use that to substitute in and determine the net force in the x direction in which the block may be accelerating to get a final expression for the net force as F cosine theta minus mu k times basically the substitution right here, mg minus F sine of theta. Now, the nice part about the definition of work as force times delta x for some constant force is that all we have to do to find the net work now is multiply both sides by the total distance over which this force applies. This means that the net work is basically this right here, the force just with a delta x multiplied through. Now, the work done by friction and the actual pulling force itself gets a bit trickier. So, we know that work equals F times delta x, and we know, basically, the distance it travels, so the work is just delta x, and we know the force, which is mu k times the normal force, which is mg minus F sine of theta. I'll just squeeze that in there, from what we derived over here. We can also determine the work, that's the work done by friction. We can also determine the work done by the pulling force F, based on how much it puts in the direction of this displacement. So we know that it's F dot R, which is simply the force times the distance traveled, delta x, times cosine of theta. And then, our last expression, if the velocity is constant, what is the net work on the block? Well, we know that work is the change in kinetic energy. And if v0 equals v final, in other words, the velocity doesn't change at all, then we know that the kinetic energy also doesn't change. So the net work, then, must be 0. So in this video, we've covered the concept of work, the work-energy theorem, as well as the interplay between the two concepts. And in the next video, we're going to be looking more at energy itself, as well as how it relates to power and the different types of energy that you can store and use.